Hello! In this video, we're going to prove the following theorem. Suppose R is a total order on A, and B is a subset of A. If B is a minimal element of B, then B is a smallest element of B. Now, before we get into this proof, I would like to mention a few things first. First of all, what does it mean for a relation to be a total order? Well, if you recall, all that means is that our relation is a partial order, and for every two elements, x and y in the set A, we have that either x comma y is an element of R, or y comma x is an element of R. And just as a refresher, what does it mean to be a partial order? Well, all that means is that our relation is reflexive, transitive, and antisymmetric. Second, what does it mean for B to be a minimal element of B? Well, there's a few ways of saying it, but we're going to say that it means for every element x in B, we have that if x comma B is an element of R, then x is equal to B. And lastly, what does it mean for B to be a smallest element of B? If you recall, all that means is that for every element x in B, we have that B comma x is an element of R. Okay, so now let's get into the proof. So let's suppose that we've already declared a total order R on a set A. And let's suppose that we've already declared a set B, where B is a subset of A. So now our goal is to prove that if B is a minimal element of B, then B is a smallest element of B. So suppose B is a minimal element of B. And so our whole goal now is to prove that B is also a smallest element of B. In other words, we're trying to prove that this statement is true. And we're trying to prove a statement involving every element in B, so give me an arbitrary element in B. I'll call it x. So now, with our arbitrary element x, we need to deduce that B comma x is an element of R. Now, to do that, notice that we have that B is a minimal element of B. Clearly, that means B is an element of B. So really, we have that both x and B are elements of B. Well, since B is a subset of A, clearly that means x and B are both elements of A. And now, because R is a total order, we know that this statement is true. And this statement works for every two elements in A. So it must work for x and B. So we can take x and replace it with the x that we have in our proof. We can take y and replace it with B. If we do that, we get that either x comma B is an element of R, or B comma x is an element of R. And we want to deduce that B comma x is an element of R. So what we're going to do is we're going to prove that in either case, we have that B comma x is an element of R. Now, clearly, if we have the case that B comma x is an element of R, then B comma x is an element of R. So there's nothing more to prove. So now we're going to consider the other case, which is if x comma B is an element of R. And so in this case, we also want to prove that B comma x is an element of R. Now, because B is a minimal element of B, we know for a fact that this statement is true. And this statement works for every element in B, so it must work for x. So if we take x and substitute it for the x that we have in our proof, we get that if x comma B is an element of R, then x is equal to B. But x comma B is an element of R, so we can conclude that x is equal to B. So, since x is equal to B, we can take x comma B and replace x with B and replace B with x. So we get that B comma x is an element of R. So notice, in either one of these two cases, we have that b comma x is an element of R. Clearly, if we have b comma x is an element of R, then b comma x is an element of R. But also, we showed that if we have the case that x comma b is an element of R, we also got that b comma x is an element of R. Because, well, we proved it right here. So in either case, b comma x is an element of R. So putting this all together, we started with an arbitrary element x in b, and we proved that b comma x is an element of R. Since x is arbitrary, this means for every element x in b, we get that b comma x is an element of R. Which means we have proven precisely this statement, which amounts to proving that b is a smallest element of b. And so this completes the proof. And so yeah, that's pretty much the idea of how you could prove a theorem like this. And yeah, that's pretty much it for this video.